Good evening to all the participants present here. We're very happy to kickstart the Celesymposium 2.0 workshop series. For the first workshop, we have Mr. Animesh Garg, a student at the University of Arizona, pursuing a degree in astronomy and a minor in aerospace engineering, to share with us the wonders of the James Webb Telescope. Next slide, please. The instructions for today's webinar are as follows. Make sure to read and follow them. Refusal to do so will lead to immediate disqualification. Please play the video.
The sponsors who have helped make this event possible are Boots and Crampons, University of Arizona, Cascade, Wolfram Language, Gen.xyz, and Interview Cake. We will now stop presenting and hand over the mic to our speaker, Mr. Animesh, to start the workshop.
Thank you so much. Thank you so much for having me. Good evening, everyone. My name is Animesh Garg, and it's a pleasure to be here. Thanks for organizing all of this. As mentioned by Mana before, I'm a second-year student at the University of Arizona. I am studying astronomy. I have a minor in aerospace engineering, a minor in physics, and maybe a minor in math. I'm not sure how that's going to work yet. But today, I want to talk to you all about what astronomy is, why we do it, what's in astronomy, and is it just because we think stars are pretty? They are. But then there's definitely more to it, right? Which is what I want to hopefully convey to you in the next few minutes. I think the slides may have gone off.
Yeah, you can screen share now.
All right, sounds good. Let me know if you can see my screen, by the way.
Yeah, it's visible.
All right, perfect. Yeah. So without further ado, let's dive right into it. Let's understand what astronomy is. So first question is astronomy and astrophysics. We've heard both of these words floating around a lot, and sometimes we get confused as to whether they're the same thing or not. So as a brief, astronomy is the study of celestial objects and the study of space matter, basically. Astronomy focuses on things that are as small as asteroid paths, and we go all the way to studying things like the Big Bang, the cosmos, and we think that the Big Bang is the beginning of time. We study all of these things in astronomy. Astrophysics is a branch of this. Now, what I mean by that is we collect data from the universe, whether that's through James Webb telescopes, whether that's through data analysis, whether that's through imaging and optics. We have multiple ways of getting this data. But astrophysics is the branch of astronomy that takes this data, applies laws and physics to it, and then we actually make analysis and conclusions out of this data. Another important question to consider is why why do we do this? What do we hope to gain from astronomy? And during the process, and during the process, there are four important things that we need to look into and understand completely: the Big Bang, the evolution of our universe, the ways in which astronomy is helping us every day, and what do we hope to get out of astronomy in the future. So, to explain this, I think first we should talk about the Big Bang itself. So, as a brief history, the Big Bang caused an explosion at the beginning of time, or so we believe the beginning of time, almost 13.8 billion years ago. When the explosion occurred, basically, when the Big Bang happened, it was an explosion through the entire universe where there's a single point in space where everything is condensed, super condensed, almost into a single point. And when the explosion of Big Bang happened, everything expanded. It basically went from being a ball to starting to expand like this. And over time, that explosion was actually less than 1 second. There's some theories as to that the time of the expansion being being 10 to the power 10 negative 30, which is basically 0.000 and 30 more zeros. After that, a 1, and counting that as the time that the expansion happened over. So it's a very small time, but it's also important to consider that the expansion that happened was even faster than the speed of light. Hence became the universe we know today, the observable universe that we see today. Um, so when this expansion occurred, trillions of particles of neutrons, electrons, and protons, which are also the basic building blocks of every atom in our universe, were also expulsed in this explosion. They were all scattered throughout the trillions and trillions of kilometers of space. Over time, the universe continued to expand. Even to this day, it's still expanding, but the rate is much slower as from what it was. But after about 9 billion years of the initial impact, our solar system finally started to form. When those atoms came together, they started to form stars. And some of those particles came together to start forming asteroids and debris. And after that, that asteroid and debris collided with each other, they fused with each other. And then after that, our solar system was made. Within that, the planets were made. And then over time, evolution took place. And then we were here. So that's the Big Bang. Now, the question is, oh, sorry, I did not realize the slide went. Yeah, so another question that we also have to ask is, which brings us to our original question, why do we study all of this and what do we aim to understand from it? So studying the space and stars and universe allows us to understand a lot of things. Firstly, where we came from. After that, how did we get here? Like, what was our evolutionary process to actually becoming humans, becoming, civilizations and beings as of today? What was the process that took place for that? And not to mention all of Wi-Fi technology as we know it today, all of GPS technology as we know it today would not be existing without the study of astronomy. The study of astronomy was the first field in history to use radio waves, to use frequency waves and bands to transmit data, which at the end of the day is the basic principle of Wi-Fi. And it's also important to ask, what do we think astronomy is going to help with in the future? So we need to understand that we're in a day and age where our Earth is changing, and it's changing very fast. Global warming is taking its own place. The expansion of the universe is also taking its own place, and the sun is also expanding. very slowly, but it is still expanding with every decade. So, the study of astronomy is, well, in my opinion, as of today's day and age, it's most useful to understand how weather cycles and sea levels are going to impact our survival on Earth. And it's going to allow us to explore the rest of the universe, to see other planets that are hospitable or similar to the structure of Earth that we can at some point try to colonize. So these are the few things that we need to take into consideration when we talk about what astronomy is, why we do it, or as I like to say, all of these things are one side. We just think the stars look pretty, and we like taking pictures of them with multi-million-dollar telescopes. Again, that is very true though. Okay, so to move on, subfields of astronomy. So here's just a list of things that we cover in astronomy. These are subsections of astronomy. Like I mentioned before, astrophysics is a subsection of astronomy, in that we use physics and the laws and theorems to prove or to calculate certain things and certain conclusions. Similarly, astrobiology's area of focus is to understand how different organisms react in space and whether or not a different planet can be suitable for us as humans, in which exoplanets is also involved, in which planetary sciences is also involved. All of these fields, in its own way, are very codependent on each other. They're very correlated. But at the base level, they all follow the same principles. So out of all of these things, what is my specialization? What do I do personally? Uh, my area of research and study is instrumentation, optics, and imaging. So when we talk about observations in astronomy and the imaging techniques that we take advantage of, it's a very wide spectrum of tools that is required to create a single image. Some of the techniques that are used are waves, rays, monochromatic scales, and with all of these technologies, images are taken in multiple forms of the same field of view. So imagine I have the sun over here. I will take maybe 20 images of the sun in different formats. And then I will use all of those images to combine them into one image and then give you a final image of the sun itself. And on the next slide, I will be showing you the different bands that are sometimes used to create images. And I'll explain the process in which we combine these images to create an image. Yeah. So over here, what I have aimed to show you is how, okay, so you will see a few bands over here, going from band 1 to band 7. And you will realize that there is a slight deviation in the color and the contrast of every single band. Some bands are darker, some bands are lighter. And some you can barely see anything apart from the lightest areas of the image. Now, all of these different bands, they're taken over different wavelengths. And after these bands are captured, after the base image is captured, we then proceed to create the color spectrum, which is red, green, and blue, RGB. We continue to create images based on these three primary colors, which we then use to combine later to form a final image. Now, what do we aim to do with this? What we aim to do is we aim to understand the brightest areas of the image and the darkest areas of the image. What this allows us to do is understand space in a more comprehensive manner, and it allows us to create a better analysis as to what we are looking at. Because the image that we're looking at right now, it is not a visible light spectrum. I will repeat, this image is created as a representation as to what we will see or as to what we are supposed to see when we take an image based on real colors. And on this slide, it's just a representation of the bands that we used in the previous slide. And these are the different bands that were used to capture images and the different bands that created those colors. Now, another big question is, what are the tools, what are the means, and how do we get so many different bands? Why do we do this? How do we create so many different segregations? The answer to that is telescopes. This brings me to the next part of my seminar today. James Webb Space Telescope was launched in 2021 with a few very certain set of missions that I will continue to explain. But it's also important to know before I continue that James Webb Space Telescope is one of the greatest telescopes ever created, and it is breaking grounds ever since it has gone up in 2021. A little bit more about this telescope. James Webb Space Telescope, it's also called JWST for short, is the largest infrared telescope with a 6.5-meter primary mirror, which was launched in 2021 with a few basic missions in place. Some of these missions include studying every phase in the history of the universe. So, going from the Big Bang and maybe even before that to studying everything till date. And the formation of solar systems capable of supporting life on planets like Earth, and even studying the evolution of our own solar system. Although JWST was launched very recently, it has still outperformed the expectations that we had in terms of image clarity and sharpness. To understand why we think that James Webb is such a great telescope, we also have to consider talking about the Hubble Space Telescope, which was the telescope right before JWST, which was launched in 1990. Now, the image that you're seeing on the slide over here is an image of a deep space view. All of those little stars that you see, somewhere or the other, you can see some circles. Those are galaxies within themselves. That is how far we can now see. Now, this image with JWST was taken over the time of 12 and a half hours. As an image similar to this and much lower in quality with the Hubble Space Telescope took us 11 days to capture, maybe even slightly more. So it's important to understand how meaningful and how impactful JWST is going to be in terms of the clarity that we get, the depth of vision that we can have with the telescope. And at the same time, we are perceiving data faster than ever before. This will allow us to understand our universe much better, much faster. And we'll have more data to compute with than we have ever had before. And so some of the most important teams that have been involved with JWST are NASA. They were the head branch for all of this. Eastern European Space Agency, ESA. They provided the near infrared spectrograph, mid-range instrument optic assembly, and the Ariane launch vehicle. The Canadian Space Agency provided the fine guidance sensor near infrared imaging and slitless spectrograph. So all of these teams came together to create this telescope over more than a decade. This was a very long project, and we expect the James Webb Space Telescope to be orbiting or at least giving us reliable, fast data for the next decade or so. Now, where does University of Arizona play into all of this? As you can see at the bottom of the screen, what did we do and why does it matter? So, if you recall, we looked at the James Webb Space Telescope, the picture of it, and next to it there was another picture. Sorry, come here. I think it's very important to understand the things that the University of Arizona is doing in terms of space sciences. And one of those key components is to understand the technology that we are given, the technology that we will continue to develop. And I chose to come here because of the opportunity that I get from being here. I get to work with people who are leading experts in the entire world with this medium. For optics and imaging, the University of Arizona is maybe in the top 5, maybe even the top 10 in the entire world. For imaging and optics, I believe it is the top in the world. That's my reason for coming to the University of Arizona. And I will say that this field, it is very taxing. There are times when I feel like there there are times when I feel like it's very stressing. It's getting too much. But then at the same time, it's a very rewarding field. It's something that I've chosen to, well, I chose to take it, but at the same time, it has been extremely rewarding, not only in terms of academia, but also the people that I've met, the professors that I've met. They're very kind, they want you to learn. And there will also be a certain point in time in your degree where you feel like you basically start to understand how much you don't know, which is when your professors are there for you the most. They start to understand that, okay, this is the problem, here is what you do, and here is what you don't know. Now let's focus on let's getting to know everything again. That's astronomy. And I think I will open the portal to questions now. Thank you very much for listening.
Yeah, thank you, Animesh. We will soon be starting with the Q&A session. Participants, please feel free to write down doubts in the chat.
Can I stop sharing from my side, or would you like me to keep that up?
Uh, yeah, you can stop the screen share. Slowly.
Yeah.
All right. So I'm just going over the chat myself, and I saw one of the questions. So the thin layer of gold is beryllium. Beryllium is an extremely reflective surface, which is why we used it to coat the entire surface of James Webb. You also must have noticed that the James Webb Space Telescope, it was structured in hexagon shapes, exactly 6 or 7 of them, arranged in a circle and then one in the middle. So there so the mirrors that we used in James Webb, they're too big to construct as a single unit. That's why we created 7 of them separately and brought them in as a hexagon shape. Now, the reason for the hexagon shape is because they interlock very well and it does not waste any space. It allows for very marginal errors and it allows for very marginal loss in data. Okay, let's see. So Vedant, to answer your question, there are multiple tools in the field of optical imaging and um, optical imaging and visualization. I think telescopes are our first point of contact because of a few reasons. We understand a lot of data from them very quickly, and we are also able to capture a lot of data in a very short amount of time. But that also means that to understand how to implement that data, we also look into radio astronomy. Now, in radio astronomy and infrared astronomy, we use waves, and gamma ray astronomy is also a very interesting area of work. So what happens is when we need to better interpret the data that we've gathered from telescopes, we use these different spectrums to capture our universe in different wavelengths, which after that we work on collectively bringing into an image. That's why when we sometimes look at an image that's released by NASA and we understand that there are depths in an image, that's not always imaging. That could also be the result of radio astronomy, if that makes sense.
Yeah, thank you. So now there's a question from Aditya. Sir, how is the reflected image formed in the mirror captured?
So what happens is the surface of the James Webb Telescope, um, it's not completely flat. So what happens is if it's in the shape of a dome, like so, and then there's a small mirror on the top. So what happens is the light that we capture from space first bounces onto the surface, and then after that, all of them are angled in a certain way so that everything meets at the mirror on top. And when this happens, the mirror is then attached to computers and microcomputers and then multiple other variable channels. And that is when we actually begin to comprehend and break down and capture data. The reflection part of it is crucial though, because any imperfections in the surface mean imperfections in our data. I hope that answers the question.
All right. Next question is by Anushka. She's asking, what are the ways by which you were able to make the camera so great and even having able to withstand outer space conditions?
So a lot of the So there's something important to understand about telescopes in general. What happens is, yes, you're right. The sun is way too bright for a lot of things to handle, which is why we take the help of heat shields. Now, the huge layers that we saw that were staggered one on top of the other in James Webb are heat shields. Those sheets are able to withstand maybe even 4 to 5 times the temperature of the sun. And having that many is both a security measure and at the same time it also allows us to make sure that the camera stays cool at all times, because what happens is, something to understand about the telescope is it's structured like this is where the camera is, this is where the bulb is, and this is the side that will face the sun. So it moves around the earth like this in such a way so that the back of the telescope is always facing the sun and the camera itself is not at harm.
All right. Shreyansh asks, what do you think is the next big thing after James Webb Telescope?
So I think right now it's too early to say, but James Webb is probably the next leading thing for the next 10 years. After this, we might be focusing on, so there are two areas that are expanding right now in astronomy. One is LIGO, which is, so in short, LIGO is one of the fields of study that is more oriented towards radio astronomy, in which we use different wavelengths to picture the universe from Earth itself, not sending out a telescope necessarily.
All right. Um, Katyani asks, can the James Webb Telescope answer questions like what are the origins of supermassive black holes?
Supermassive black holes are something that are not necessarily covered in infrared technologies. Infrared technologies are more centered around the development of certain things rather than the imaging of certain things, which is why telescopes like the Event Horizon are better suited to answer questions for black holes. What we aim to do with James Webb is to go maybe a little bit back in time to understand how our universe formed, where we originated from, and to predict future paths, not necessarily to image the universe.
All right. Samantha is asking, for how many years can we use the James Webb Telescope?
So we predict, so when it went up, we did create a prediction for about the next decade or decade and a half. But in the event that something goes wrong, that could shorten. In the event that nothing goes wrong, that could go even longer. I think that's one of the most variable things about space science. Something that no one has a definitive answer to, I think, unfortunately. But the expected duration is 1.5 years. Sorry, 1.5 decades.
Um, Panya is asking, she's asking you to repeat how the planets were formed again.
Okay, so When the Big Bang occurred, so everything started off at a single point. Everything was super condensed into one point. Everything was super, super, super condensed. Like it was almost infinitely dense. And when the Big Bang happened, everything expanded, not exploded, expanded. And when it expanded, the universe basically went like this outward, and then it also expanded like this. So it became almost like a cylinder going outwards, if that makes sense. And what happened because of that is there were trillions of particles of neutrons, protons, and electrons that also got scattered across the universe. Now, over time, this was 13.8-ish billion years ago. And what happened after that is they slowly started to condense over the next 9-ish billion years or so. And then after that, they started to form clusters of galaxies. In those galaxies, you started forming asteroids, you started forming stars. And over time, the debris that was the asteroids, they started to collide into each other and they started to fuse into each other. Now, what happened over time is that just became bigger and bigger and bigger. And there was actually a point in time when our moon would not have existed unless, so there was a certain point in time, almost 4.5 billion years ago, around the time of the birth of the Earth. So this was Earth, and imagine this is sun somewhere distant over here. The moon actually collided, it was an asteroid that collided into the Earth, and then they fragmented. And after that, it slowly started to form into what we now call the Earth and the Moon, which is which is quite fascinating actually, because the moon would have never existed, and the moon controls so many things for us, like our tidal waves. It controls some part of our gravity as well. We may have never existed if the moon was not an asteroid that collided into Earth. So I think that's also very important to understand and analyze within itself. And over time after that, once they started to cool down, asteroids kept hitting the Earth. And with that, they brought water. And then after that, evolution just started to take its own process, its own time.
All right. Manu asks, was James Webb Telescope used to capture the image of Sagittarius A?
Sorry, could you come again with that?
Yeah. He's asking whether James Webb Telescope has been able to capture an image of Sagittarius A.
I can check. I Sagittarius.
That's all right. That can probably be Googled. Moving on.
Oh, I
We
see. Okay. This
yeah.
was actually done by the Event Horizon Telescope. This was not something that was involved with James Webb. I think the image, the black hole that you're referring to, was first imaged and or discovered in 2019 by Event Horizon.
Okay. Um, so there's a question from. Okay, so there's a question. Space telescopes are more efficient than ground telescopes, and then why do we continue to have more number of telescopes in comparison to space telescopes?
The function of ground telescopes is more than just understanding space in science. It also allows us to map certain things. So what happens is, okay, so more often than not, we create a prediction as to where we presume a certain object will be or a certain galaxy will be. So imagine I have two stars in the sky, one is about here, one is here. Now I know that between these two stars, somewhere along this band, I'm looking for a particular galaxy. Now, in that particular galaxy, I'm looking for a certain planet. Now, it's very hard to calibrate such fine maneuvers if you have a telescope that is continuously moving in space. So, what we do is we create, and the reason for so many of them existing is because in our northern southern hemisphere of the Earth, you don't. Okay, so if you are above the northern hemisphere of the Earth, you don't always see stars that are existing in the southern hemisphere. And when you're in the southern hemisphere, you don't always see stars that are in the northern hemisphere. So you need telescopes on both sides, and the telescopes on each side, they basically allow you to capture that half of the hemisphere, if that makes sense. And I think that is one of the biggest reasons why we have so many ground telescopes and not as many in space telescopes. Another reason for that is the amount of money, the amount of resources that we would actually need to get one of these telescopes off the ground into space. James Webb is a telescope that is made of extremely light material. And even then, it took billions of dollars to fund it to actually send it up. If we were to do that with maybe there's an observatory called Kitt Peak, which is one of the biggest observatories in the world. I don't even think it would be possible in today's day and age to actually send that to space.
All right. There are many participants who are inquiring about James Webb and its, contribution towards dark matter and dark energy. Is there anything pertaining to that that you can elaborate on?
Yeah, I was expecting that question to come by at some point. So, JWST and dark matter is something that unfortunately I don't know too much about, but all I do know about it is that it's continuing to observe dark matter. It's continuing to take data in the field of deep space imaging and deep space viewing. But what we do with that data is something that unfortunately even I don't understand yet. Hopefully, I'll understand it by my fourth year, but let's see how that goes.
All right. Okay, this is quite interesting. There is one question about, right. This question says that James Webb Telescope creates images of past events. So they're asking how is that possible? How can we look into the past when we look at these images?
So, okay, I think the best way to explain this would be through Interstellar. For those who have seen the movie, um, the main actor of the movie goes into space, goes near the speed of light, and then comes back to Earth in his mind 10 years later. But as per Earth, almost 100 years have passed. So basically, in that movie, at the very base concept of it, it talks about traveling near the speed of light. And the speed of light is 3 into 10 raised to the power 8 meters. That's um, that's about 30,000 kilometers per second, I believe. Yeah, that's 30,000 kilometers per second. Now, when you go that fast, the laws of physics, they start to bend a little bit. The way time is perceived, the way time carries itself is also slightly different. And when you look that far into space that quickly, you also see images. You don't necessarily see images from the past, you see what they would have been, and you see the evolution through that perspective. The Andromeda galaxy, we it's so far from us, and that's the closest galaxy to us, by the way. Andromeda is the closest galaxy to us. Um, if it were to disappear today, we would actually not realize it until almost 2 billion years later. It's that far. That's how far the light has traveled towards us. So that is why when we talk about imaging in space, it's not in the past, but that is how long the light has taken to travel to us.
All right. There is one question about so the participant says that they've always had this question about telescopes, which can capture such clarity. Is it all about the glass in the telescope, or does it also depend upon the type of sensor they use?
It's a
Like the
combination of both.
all right.
But a lot of it falls down to the clarity, the cut, and the quality of the materials that we use while constructing the telescope. And the processor itself is the secondary step. because more often than not, we actually have a secondary or a backup sensor on board. But if something is to happen to the actual surface, there's no way to go up and fix that.
I see. All right. There's another question. We don't know whether a cosmic galaxy still exists in the universe. As the photo is capturing the light, which is nearly from 13.5 billion years ago, which is really near the time of cosmic inflation. So, can we tell whether the cosmic galaxy still exists or not?
So, okay, cosmic galaxies. I honestly don't know too much about that. I can get back to you about it, but even I'll have to look into that one.
That's all right. There's another question about whether the orbit of the James Webb Telescope really, matters for the imaging of the space.
To some extent, it does, but then at the same time, we are also capable of aiming the telescope in a certain way where we can focus on a certain object or a certain field of view for a continuous amount of hours. So we can make do with it. It doesn't severely hamper us in any way, but if there was a way to fix it in one point in space, that would be pretty nice.
Right. All right. There's this one question about how the James Webb Telescope will help us to understand the formation of the universe and whether it will give us a view of the history of outer space before the Big Bang even occurred.
So that's a theory that we're looking into. That's something that we don't have a conclusive answer to yet. We think that it's powerful enough to view before the Big Bang. If it is, then it would explain a lot more as to how we even got to that first initial um, expansion of our universe, which would be very interesting. But we don't have conclusive proof yet as to whether that's going to be possible or not. And it's believed that it will be because this telescope is almost 6 to 7 times more powerful than Hubble. And we hope that through it we will be able to get into an answer for that as well.
Okay. So there's a question. Can you explain the working and making of those heat shields? And can JWST give us some more theories about the beginning of time or any proof against or of the Big Bang theory?
So I'll answer the Big Bang Theory part of the question first. So the Big Bang Theory has already been proven. It's not something that is a theory anymore. It's actually something that was proven a few years ago. We know that it happened. Question is, why did it happen? Question is, how did it happen? That's something that JWST could help us with. But as far as the question goes, will it support the claim that it happened? Answer to that is no, because we already know that it's happened. And for the first part of the question, which was how are the heat shields formed? Um, Honestly, I think the heat shields are so the heat shields are basically aluminum sheets that are layered with Captain E. Now, Captain E is a certain form of chemical, a certain form of it's a certain substance that is combined with silicon and it's used to coat aluminum sheets, and that creates a heat shield.
Okay, so there's a question. Some scientists say that the Saturn's largest moons are inhabitable. Is this true? Like, and if it is, will we be able to colonize it? Sorry, it's
So
habitable.
yeah,
Yeah, continue.
Saturn's moons, yeah, okay, as far as I remember, Saturn's moons have been shown to one or two of them have showed some signs of being able to support life. But that doesn't mean that they're completely habitable for humans yet. We're still about to draw more conclusive results on that. We have found some traits or characteristics that may point us in the right direction to tell us that life may be able to exist on here. But whether or not it will actually exist, I think is something that we're still about to find out, something that we need much more data to calculate.
All right. We'll be taking last three questions. The workshop time is exceeding now. Okay. There's just one question that asks, can you patch updates in the James Webb Telescope just like the Hubble?
Um, I'll have to look into that. I think I do have it open with me, so I can just look into that right now. Um, yes, I think the short answer is yes, we can.
All right. On a bit of a comedic note, there is one question that asks, do you think the interstellar is scientifically correct?
um, okay, so there are some things in that movie that I absolutely love. It's a beautiful movie. I enjoyed it a lot. But as far as the imaging of the movie goes, there's a lot of debate across it. They take a very interesting dive into the whole concept of singularities and how time and space warp around each other and how the existence of wormholes exists. That's debatable. We're still looking into that. But as far as talking about singularities and how space and time wrap around each other, it's a very surface level interpretation, but it's a very interesting one. It's something that is a theory even today as to how time and space act differently around singularities like black holes.
Okay, there's a question in the chat. With the future coming faster than expected, how do you think artificial intelligence will be helpful in this field, and what would be its probable applications be?
So AI is already helping us in astronomy. That's something that should be known. AI is a field that is helping, I think, in just about every sector now. I don't think there's a certain area or field where AI is not used. In terms of astronomy, one of the biggest ways that we use not only artificial intelligence, but also we use computational data is to draw multiple thousands and maybe even hundreds of thousands of conclusions. And we use them all to simulate or recreate what we think will happen over the next few decades or things that have already happened. So the whole concept of how the Milky Way is a spiral galaxy, there's a certain part of computational data involved in it. And the clarity that we have now, based on multiple factors, there was a lot of AI that was involved in actually recreating the base image to understand that, yes, it is a spiral. And at the same time, these are the key features that distinctly tell us that it's a spiral. So AI is something that is already being used. It will continue to be used. How exactly? I'm not sure. AI could be used to help us with computational data. It could be useful in terms of helping us to interpret new data. And it could also take pre-existing data and create a new conclusion altogether. So the limits of AI are unknown, but the application is even further unknown. And that's a good thing and a bad thing.
All right. Last question. Okay, this is a relatively interesting one. I guess you've all heard about the white hole theory. So there is one participant who asks if all black holes are connected to a white hole if they do exist. And would that make any logical sense?
Um, okay, so basically the basically the whole concept of that is, I believe, the neglected twins. There was a theory that was introduced based on this. Um, to be completely honest with you, we don't know yet. As far as we know, black holes are a singularity out of which even light does not escape. But the existence and the theory of white holes, that's something that honestly I don't know yet, something that I may not have crossed yet, but it's an interesting concept. It's something that's intrigued me as well. Um, and I want to learn more about that field as well.
All right. I guess we have 2 more minutes, so we'll just squeeze one last question in. Sorry for
Yeah,
that.
sure.
How does cryogenic cooling work on the James Webb Telescope, and how will it be possible to carry this out with the same systems over 10 to 15 years?
So the whole concept of cryogenic cooling. So there's a few methods that take place in cryogenic cooling, and the base of it is based on liquid nitrogen and or solid carbon dioxide that is stored, in a direct compartment storage. So when we put when we introduce these systems on board on a mechanism or a telescope, in our case James Webb, we make sure that we give it enough reserve to be able to last 10 to 15 years. We take into account that um, the solar flares, the heat radiation that we will experience. We also take into account a lot of other factors to draw a conclusion that, okay, this is how much we will need for this duration of time. But again, these are all just calculations. These are all things that we think will allow us to continue, because at the end of the day, space is unpredictable. If there's ever a major solar flare, or if there's a asteroid storm that is headed towards us or headed in the direction of James Webb, and if that happens to hamper something on the um, technology itself, then that could be cut short again. But to answer the question of how do we know it'll last 10 to 15 years, we give it enough reserve storage to presume it will last to 10 to 15 years.
All right then. That's all the questions we'll be having for now. Let's not hog our speaker any longer. Um, if you guys still have any unanswered questions, we'll be further sharing the PPT and an additional document for you guys to consult. Hopefully that will answer all your doubts and queries. Thank you, Mr. Animesh, for the great session today. We really had a lot of fun. It was quite insightful. Thank
Thank you
you.
so
Thank
much
you
for
all.
having me. Y'all have been a wonderful audience. And yeah, I'll be sharing that document with you shortly. Share it with everyone. And I hope that you all find some answers that even I don't know.
Thank you. Thank you so much, sir.
All right. Thank you so much. Have a great evening, everyone.
Same to you, sir. Thank you. Thank you to all the participants for joining. You may just stay for a few more seconds. We'll be